Good afternoon. Thank you, Mr. Chairman. I'm Jaime Planas, and this work has been carried out with the collaboration of Beatriz Sanz and Professor Sancho, all from the Universitat Politécnica de Madrid. And since we have very few time, I will work like a child, and point Einstein. So quasibrittle here means no large scale plasticity. Think about concrete. And macro defect free means no defects larger than grain size. So this is what I'm trying to simulate computationally. So I will talk about the motivation, the tools we use, and two examples to end up with final remarks. The motivation basically is that we found years ago that in a three-point bend specimen like this one, it was necessary to have some kind of inelastic behavior around the main crack in the center. We simulated that with Rankine plasticity, but nowadays we use another method. Now, this is a result of a specimen which was tested by Beatriz Sanz, a main crack you can see here, but there are other secondary cracks, and before that there are many other small cracks that grow everywhere, about everywhere, and then start to localize until we have a final pattern which is very similar to the one we find experimentally. So it's only a few main cracks survive. Now the question arises about whether the method is reliable and is robust. So what we did is to use our model with very simple cases to see what happened. So this is the initiation of the research. We use a finite element framework, which is continuum-oriented finite elements that are object-oriented and generic. They have vector and tensor algebra. They have cohesive cracks. They have finite element with embedded cohesive cracks, and use Gmesh for input for photographic things. The basic ingredients of the model we use is the cohesive crack model. We use constant strain elements. With these, inside the elements, we have a strong discontinuity kinematics, which I don't have the time to explain. We use local crack equilibrium, which is equivalent to a return algorithm in plasticity. And we extend a little bit the model to avoid crack locking with limited crack adaptability. What I want to emphasize is that the computational method is strictly local. Only information of each element is necessary. Okay? There are no tracking or tracing of any kind. So this is a mesh in 2D in which the red line are the cracks inside the elements, and one element has the crack with the traction, cohesive traction, and cohesive crack opening, and the orientation, of course. Then the cohesive crack model is a cohesive crack with central forces. At the beginning, we use that just because it is convenient, because of the lack of data usually for mixed mode. But now we know that it is also necessary for framing defects. There is a paper by Costanzo where this is proved. So we use central forces. We use a softening curve with unloading to the origin, and the full equation is that one is not necessary to explain traction proportional to crack opening vector, and this is the traditional one-dimension softening curve which can be obtained from mode 1 tests. So this is one of the ingredients. I don't have the time to explain the others. So the first example is a notch beam. Depth to notch, no notches, span to depth ratio of 4. A nominal stress just to plot the results. We measure, what we plot is the relative horizontal displacement between those 2 points. And the softening curve we use is the same used by Arbilla. And with these 2 parameters, tensile strength and this displacement, crack opening, we can form a length scale together with the elastic modulus, which we call the second characteristic length, which is more or less equivalent to Hillerborg characteristic length and to Irwin's length. So, in the following results are for depth of the beam of 0.15, the second characteristic length. So let's see the numerical aspects. Only one size, I will present for only one size, 4 mesh sizes, 3-step sizes, and this as a mesh, coarse, finer, finer, and the finest. Okay? N is about the number of elements on the depth. So, the observable results at the low, what we can measure in the lab is the low displacement curve. And for the 4 meshes, they are pretty much the same, and there is no mesh effect. Moreover, this is for 53 steps. If we go to 5 steps, or to only 1 step to go to that point, we get convergence and we get perfect results. So there are 5 points here, crosses, and only 1 point, in only 1 step. So it seems to be robust enough to use nearly any step. Now, curve propagation, which is the interesting point. I present the results from step 10, 11 up to 24, but not all the steps, just the steps that had a difference. For the finest mesh, at the beginning, there are many cracks, the tensile part of the specimen. Then these cracks grow, they grow and get sparse, and the sparse, and one localizes on the right. But then in the next step, there is another crack on the left. There are 2 cracks, and after that, only one can survive, and that one is the one on the left. Okay? So this grows up to step 24. And that's it. And then we are just after the peak, and then only one crack is growing. If we use the other mesh, I will show only 5 of the results. It begins more or less the same, except that it is much coarse, and then we cannot see the same fine things. So in step 16, we start to see step 15, we start to see the 2 cracks. In step 16, we have exactly the same 2 cracks, and now only the left crack survives. And basically, in the last step, we have the same far field and the same crack. And this is for a case in which we know that only one crack can survive. Now we show a second example, which is a shrinking slab very, very simplified. This simulates an overlay over an existing substrate, which is taken as rigid. We have vertical displacement allowed at the ends. So it is a uniaxial, classical uniaxial problem. And what we have, we define the problem as the shrinkage stress or nominal stress, which is the surface stress it would have if there were no cracks. So for the elastic solution, we can simulate this for thermal shrinking, for example. The only thing is that there are at least two geometrical sizes and also the characteristic length. So to simplify further the problem, we take a linear softening. This is the second characteristic length, as I said, and we use a linear shrinkage profile in which the surface stress is increasing from 1 to 4 times the tensile strength. And we use only one size, which is 0.3 L2. Then this is the mesh. It is quite fine. This is an expansion of the central strip. And with this, let's see how the cracks grow and localize. So for 30 steps, excuse me, here there is the factor multiplying the tensile strength, and the dark red is the tensile strength, and the dark blue is zero stress. Then what we see is that at the beginning there is one crack per element. So it is nearly pure plasticity, Rankine plasticity, perfectly uniform. Then when we increase the steps, the plastic zone, let's say, increases, the cracks are very little open, less than 1 nanometer, and when we reach a factor of about 1.5, we start to see that some cracks are protruding with respect to the others. And this is increasing, and cracks start to get localized. Quite a few, more than 12. But then this progresses, and those cracks, some of them start to disappear, and when we get to 2.9, more or less the final structure is already reached. This is for 3.3, the final point is 4, and this is basically, the pattern is the same. It is deeper for 4, but it is the same. We have 7 main cracks, and the few secondary cracks, all of the remaining cracks have disappeared. When we use 6 steps, this is for the second step in this part, we have more or less the same thing. This is for 2.5, for 3, we already have a pattern, 3.5 and 4. And at the first look, it is the same. But if you look carefully, it is the same up to more or less here. But this part is different. Not exactly equal to the one in the first simulation. So the overall sensation, overall impression is that it is the same, but it is not the same in detail. And for 3 steps, well, someone decided that it was time to finish, so I will have to finish, because there is apparently no other, there was another transparency, if you don't mind. These are the conclusions, which say that the present is a strictly local method that captures the transition from distributed to localized cracking, that is basically insensitive to mesh and to step size, seems to be robust since it comes to a solution for any step size, but it has some problems which are not so important. The details of the localization do depend on the mesh and on the step size, and also that it would be interesting to find the invariant statistical parameters of the crack distribution to decide if the distribution is statistically similar or not. And with this, I get to the end, and thank you for your attention.